Okay, so now you should be world experts at common sense and able to use preferably my method that I showed you for drawing Lewis structures pretty much for anything. But now there's a few issues that we need to add to, some refinements that one can make when one is drawing Lewis structures, and then we'll talk a little bit about some of the big problems and issues with Lewis structures. But first of all, some of the refinements. So I sip my coffee, and let's introduce you to the R word, resonance. This will be a word that will strike fear to you when you get into organic chemistry. They look at it slightly differently than we do, but if you can understand these next few slides, hopefully it will help you when you get there. Let's go back to our structure of SO2. Okay, if you remember when we did it, we got to this stage here with 20 dots. There were 18 valence electrons, so we had to reduce the number of dots. And the way we did that was we would take two atoms that were already bonded and had lone pairs, and we would remove the lone pair or a lone pair from each of those atoms and add a bond. Okay, now I kind of glossed over it when we were doing it, but I had a choice. And that's one of the big things to remember with resonances, when you have a choice of where to put bonds. Okay, now what I mean by that is the sulfur's got to be involved, but I could have used this oxygen, call it the left one, this one, the right one. Okay, I could have done either double bond there or double bond there. Okay, so I could have drawn two distinct Lewis structures, right? The one where I picked the left-hand oxygen, the Democrat, right, and I would get this picture, and that ultimately was the one I chose, right? Or I could have gone with the Republican and therefore had the double bond there. So have a look at those pictures, make sure you see exactly what we've done. Okay, now both of these are identical Lewis structures, even though they look weird, because they're both showing us the same molecule, right? They're showing us a sulfur that has a lone pair that is double bonded to an oxygen and single bonded to an oxygen. Okay, so now from that kind of Lewis structure, we would have expected to see one short and one long bond, right? Remember that double bonds are shorter than single bonds. So in whatever technique we use to look at the structure of SO2, we should have seen a short bond and a long bond, right? Short bond, long bond. However, the reality is that when you actually look at SO2, you see two equal bonds, right? That are in between a single bond and a double bond. Well, how is that? And the answer is that the way that we take our Lewis structures and we model reality is we say that reality is an average of those structures. So let's take our two structures here and let's average them together. Okay? Now when we do that, we get this purple. By the way, aren't you so impressed by that animation? I think I'm brilliant at animations for that. I cannot tell you how happy I was when that worked. But anyway, what we got here is we got the red average with the blue to give us purple. Okay, sulfur still has lone pair. Okay, sulfur is still bonded to two oxygens. But now instead of it being a double and a single or a single and a double, I'm showing it with this little, there's a whole line and a part line. Okay, somewhere in between, right? And if you think about it, that's what I would get when I average. If I go to this left-hand oxygen, here it's a double bond, here it's a single bond. This is the average. Here for the right-hand oxygen, single bond, double bond, what's the average? There is the average in between. Okay, resonance is where you have an average of more than one Lewis structure. It's very important that the central atoms have the same electronic structure. What I mean by that is that the sulfur in the resonance, as well as these resonance forms, right, but in the average structure it has a lone pair and it's bonded to the two oxygens. The oxygens, the terminal atoms, we don't care about them. If you notice that here this has got two lone pairs, over here the left hand one has three lone pairs. We don't care about averaging those terminal atoms in terms of their lone pairs. It is very important that we maintain the same central atom electronic structure there. Okay, as I said, terminal atoms vary with their lone pairs. Who cares? We can't change the connectivity. You've got to have the same atoms bonded to which. Okay, what's changing though is because we had a choice of whether to put the double bond here to the left hand one or here to the right hand one. What changes from each Lewis structure is how the atoms are bonded. Are they single bonds, double bonds? Okay, and then that bond order, right? Remember, bond order for a single bond is 1, for a double bond is 2, for a triple bond is 3. The bond order in this is actually the average of those bonds. So in this case here, we had a double bond and a single bond, right? Double bond and a single bond to the left-hand one. Double bond and a single bond to the right-hand one. You average those, bond order is 2 plus 1 over 2. So in this molecule, we have a bond order of 1.5, right? It's between 1 and 2. 1.5, because it is the average of a double bond and a single bond. Nitrate is a good fun one, and this will give me some pretty pictures. Okay, let's go through and draw the Lewis structure for nitrate. Step 1, the valence electrons. We got a nitrogen with 5, 3 oxygens, 6 each, that's 18. The negative sign means 1. 24 valence electrons in this. We have to have 24 valence electrons. Okay. Step number 2 with the connectivity. Nitrogen is less electronegative than the oxygen. Step number 3, we'll put in all the dots. And what we find when we put in all the dots is that there are 26 dots. And 26 is of course greater than 24. So now what we have to do is we have to take our 26 dot structure, this one we don't like, and we're going to have to remove a lone pair from the nitrogen and then a lone pair from one of the atoms to which it's bonded and replace it with a double bond, where you can see we've got 3 choices of oxygens to do that with. We can do the red one, we can do the blue one, we can do the green one. Okay, so let's try the red one first of all, right? If we take that, then now we've got the double bond to the oxygen. Notice the lone pair of the nitrogen has gone, the lone pair of the oxygen has gone. Okay, if instead of doing the red, let's do it with the blue. So there you have the blue is the double bonded one. It's lost one of its lone pairs. The nitrogen's lost it. And of course we had a premature click there. We could do the same for the green. Green going in, double bond there to the green. Again, nothing, no lone pair on the nitrogen, only 2 lone pairs on the oxygen. Okay. Now all of these 3 structures have the requisite 24 dots. Okay, but again, what we see in real life is we don't see any one of these things. We see the average of the 3 of them. Okay, and when we average the 3 of them together, we would get this. Okay, don't worry about the dots around the oxygens, the lone pairs, we don't care. What's important is the nitrogen has no lone pair in any of these structures, so it has no lone pair. It is bonded to the 3 oxygens. There we are, bonded to the 3 oxygens, and in each case that bond is the same, because to the red one you've got a double bond or a single bond or a single bond, so that's a double and 2 singles. Okay, to the blue one you've got a single, a double and a single, that's a double and 2 singles. To the green one you've got a single and a double, that's a double and 2 singles. So the overall bond order in this dot dot dot, right, will be 2 plus 2, right, the double plus 2 singles over now 3, because we're averaging over 3 structures or 3 positions for the bonds, and we get that the bond order is 1.33 or 4/3. One of the most important molecules in organic chemistry is a great example of resonance, and it's also an example of resonance in which we could just have followed common sense. Both of the 2 we've done already, SO2 and nitrate, we couldn't use common sense. Okay, but if we take benzene, we can use common sense. Okay, now benzene, C6H6, it's actually a 6-membered ring. Now remember, you normally don't have rings unless you've got lots of carbons. Well, we got lots of carbons. Okay, now when you look at this, we have alternating around the 6-membered ring double and single bonds. Okay, so each carbon's got its 4 bonds, each hydrogen's got its 1 bond. But when we were drawing it, I could have put the double bonds here, here, and here, or I could have put them there, there, and there. Okay, you see how everything else is the same. It's just a question of a choice of where to put those double bonds. Okay, make sure you see what I've done there. So what do you think reality is? You think we see these alternating single and double bonds when we look at it? No, we see the average of it. Okay, and again you've got these in between bonds, right? They're not single, they're not double, they're the average, they're in between. A lot of times you'll see this depicted in this way with a little circle inside that hexagon. Okay, so you see this, it's telling you that it's the resonance average of these two resonance forms. Okay, what's the bond order here? Well, it's exactly the same as we saw earlier for the SO2. Each position is either a single or a double bond, right? Double or a single bond. So we got bond order is 2 plus 1 spread over 2, so therefore the bond order for each bond is 1.5. Okay, resonance is an extremely important concept. It's one that you'll see throughout. At this class, what we say, well, the resonance is a possibility if you have choices of where to put these extra bonds. Okay? Now, another concept that's very important to organic chemists, but not to anybody else, is the idea of formal charge. Okay? Formal charge is an artificial concept for distinguishing, help us to distinguish which resonance structures are better. So what that means is, first of all, we apply it to individual Lewis structures, not the averages. Okay, so as you'll see in a minute, when we're doing it for SO2, we're going to do it for one of those SO2 Lewis structures that has a double bond and a single bond, not the one where it's all averaged out. Okay, now what you do in formal charge is you throw electronegativity out the window, you throw oxidation numbers out the window, you throw polar bonds out the window, and you just assume that a bond that has 2 electrons, each atom gets an equal share of that. Okay, so what we're going to do is we're going to effectively add up for each atom in the picture how many electrons it's got. Okay, saying that every bond it has, it's getting half an electron of each of those electrons in the bond. Okay, every lone pair it has, of course, that's completely it, so it has that. And then we're going to see how that affects, how that compares to the number of valence electrons with which it started. And the sum of the formal charges equals the overall charge. Now, before I start, I'm going to say something for the first time, and I'll say it several times again. If an atom obeys common sense, its formal charge is 0. Formal charge is only applicable where an atom is not obeying common sense. Okay? So with that in mind, let's look at our SO2 picture. Okay, we've got 3 atoms in here. Each atom gets its own formal charge. So we'll start off with this little oxygen here. Okay, the way I would analyze this oxygen, I would say it's got 4 electrons that are in lone pairs. 1, 2, 3, 4. In other words, all of those electrons, those 4 electrons, they all belong completely to the oxygen. It's not sharing it with anything else. Okay, now it's also got 4 electrons around it, but these are bonding electrons, so therefore it doesn't have the whole of each bonding electron, it only has half of a bonding electron. So when we add up the electron charge that this oxygen formally has, it has 4 electrons for the lone pairs, and it's 4 times half electrons, or 2 electrons, for the ones in the bond. So formally it has 6 electrons. Okay, 1, 2, 3, 4 from there, and then 2 halves from this bond, 2 halves from that bond. Okay, and of course oxygen started with 6 valence electrons, so it started with 6, it's formally still got 6. What's that charge? The charge is 0. So the formal charge of this oxygen is 0, and I want to point out this oxygen obeys common sense. It's got 2 bonds, 2 lone pairs, right? Formal charge is 0. Let's go to the sulfur. Okay, with that sulfur there are 2 lone pair electrons, right? Those belong completely to the sulfur. There are 6 bonding electrons, right? 2, 4, 6, and it only has half of those, right? Remember, we don't care about electronegativity, we don't care about bond polarity. We're saying it gets exactly half of each of those electrons, okay? So 6 bonding electrons, that means it's got 2 times 1, 6 times a half, add that up together, and you have that the sulfur formally has 5 electrons. Now the sulfur started with 6 valence electrons. In this picture, it only has 5 valence electrons, and so the formal charge is 6 that it started with, right? Lost 1 to give it 5, so therefore its formal charge is plus 1. Now finally, let's look at this right-hand oxygen. It's got 6 lone pair electrons, 2, 4, 6. It's got 2 bonding electrons, of which it gets half each. So 6 times 1 plus 2 times a half means it formally has 7 formal electrons. Oxygen starts with 6. Well, if you start with 6 electrons and you gain an electron, you end up with a formal charge of -1. So analyzing SO2, right, we would say that this oxygen has a formal charge of 0, the sulfur is +1, and the oxygen has a formal charge of -1. Let's use this idea to actually help us decide on what is a good Lewis structure for something. So let's do this for N2O. Right, we can't actually apply common sense to N2O. If you tried to do it, you could draw a little triangle. Triangles suck. Okay, so therefore we're going to go into the model. Step number 1, we need valence electrons. We've got 2 nitrogens, 5 each, that's 10. Oxygen has 6 valence electrons, 10 plus 6, 16 valence electrons. Go to the connectivity. Well, we could either do it NON, which is what some people do because it looks nicer, or we go NNO. Which one's correct? Well, 2 clues. First one is nitrogen is less electronegative than oxygen. It goes in the middle. The other clue is that, of course, non is the French for no. This is not the structure. Okay. Right, step 3, put in the dots right there. Okay. Single bonds everywhere, and then the terminal atoms get 3 lone pairs. The nitrogen in the middle gets 2 lone pairs. We count that up and we have 20 dots, which is less than 16. So we've got to reduce the number of dots by 4. Remember how we do this is we reduce the dots by 2 each time. Okay, so let's look at all the possible ways in which we can do that. Here is our 20 dot structure, and I've colored the atoms red and green. Okay, well, what we could do is we could, for this first set where we lose the first 2 dots, okay, is we could do a bond between the nitrogen and the nitrogen. So in other words, that's lose a lone pair from the nitrogen, lose a lone pair from the central nitrogen, or we could go between the central nitrogen and the oxygen. So that would be lose a lone pair there and lose a lone pair there. So we got 2 possibilities, right, for what we're going to do when we lose the first 2 dots. We can go with the red one, double bond to that. We can go with the green one, double bond to that. Both of these structures have 18 dots. Okay, well, now we got to do the whole thing again because we want to get down to 16 dots. Now you can start to see the permutations start to mount up. Okay, well, the first thing we could do is we could again say, yeah, let's do these nitrogens again. We know we got to lose this lone pair from the nitrogen. The question is, are we going to do it from the other nitrogen or the oxygen? So let's try it from the other nitrogen. So now we have a triple bond between the nitrogens and still a single bond to the oxygen. Alternatively, we could take this structure that has the double bond to the nitrogen and say, let's balance it all up. Let's make it symmetrical and do a double bond to the oxygen right there. Okay, you following what we're doing? So that's the 2 possibilities for the 16 electron from this 18 dot one. Okay, now let's approach this one where we took the first pair, put the bond in between the nitrogen and the oxygen. So again, we've got 2 choices. We can either, we know we've got to lose this lone pair from the nitrogen. The question is, do we bond to the other nitrogen, or do we bond to the oxygen? Bonding to the other nitrogen actually just gives us this picture. Okay, bonding to again the oxygen, so throwing in an extra bond here, right, gives us this picture. All of these have 16 dots. Which is the right one? Is there a right one? This is so confusing. Let's become history majors. Well, what you do is you assign formal charges and then you analyze those formal charges nicely. The idea of the formal charge argument is that atoms don't want to have big formal charges. Everything, common sense, again, if an atom is following common sense, boom, formal charge is 0. End of discussion. So that's obviously the best situation. The further away you get from a formal charge of 0, the worse it is, according to the formal charge people. So let's go through and assign formal charges, shall we? First one here. Well, this first nitrogen, I'd like you to see that it obeys common sense. Nitrogen with 3 bonds and a lone pair, formal charge is 0. This nitrogen, okay, it starts with 5 valence electrons, so remember 5, and then it's got 1, 2, 3, 4 electrons in this molecule. It's got 8 bonding electrons, but only has half of those. Okay, so that's 4. 5 at the start, now it's got 4, formal charge of +1. The oxygen starts with 6, remember the 6. What's it got here? It's got 2, 4, 6 all to itself, and then 2 halves from the bond, so that's 7. So started with 6, it's got 7, formal charge of -1. So that's not too bad, right? A 0, a 1, and a -1. Let's go over to this one. What I should have said is assign the formal charges yourself before you click or before you carry on. Pause or do something with it. Anyway, so starting off here, this nitrogen, 2, 4 all by itself, and half of 4 is 2, so 4 plus 2 is 6. Nitrogen starts with 5. Start with 5, now got 6 minus 1. Okay, this nitrogen has a total of 4, right? 8 bonding, of which it has half each, so starts with 5, now it's got 4, so there we are, it's got a formal charge of 1. And then this oxygen, again, let's use our nice little thing there, right? It is a common sense oxygen, 2 bonds, 2 lone pairs, formal charge of 0. So that's not bad either. Which is better out of these? I don't know. We'll talk about that in a minute. Now let's get to this last one, okay? And like I said, again, take a little while, pause it, and assign those formal charges and see if you get it right. I could always kind of get a little recording of the theme from Jeopardy or something, couldn't I? Do. That's why I don't sing. That's why I'm a chemist. Alright, so anyway, I'm bored. Let's do it. So we look at this first nitrogen. Starts with 5, right? You got 2, 4, 6, and 2 halves. 6 and 2 halves is 7. Starts with 5, has 7, minus 2. That's pretty ugly. Here we got nitrogen, right? Starts with 5, and now it's got, again, 8 electrons in the bonds, 4 bonds. Half of 8 is 4, so 5 minus 4 is 1. And the oxygen starts off with 6. It's got 2 all to itself, and then 2, 4, 6 halves, so 2 plus 6 halves is 5. Starts with 6, got 5, now it's got 1. Okay? So, which of these is the best? Well, the way the formal charge people argue it is that this first one has an okay formal charge. Okay? It'd be nicer if everything was 0, but you're just not going to get it. Okay? And the atom that's negative, the atom that's more negative is the oxygen. Well, oxygen's more electronegative, so therefore you'd say it's probably better if it's negative. Okay? Next one here. Okay, formal charge again, the same split, but now instead of the negative being on the oxygen, the negative is on the nitrogen. So the argument would go that because oxygen is more electronegative than nitrogen, oxygen would rather have that negative one. So therefore this is the second best. But the argument is that N2O would be a mixture of both of these. A little bit more towards that one than this one, but it would be a mixture of them. This last one sucks. Bad formal charge, got the -2 on a nitrogen. That is the worst charge by a long way. Right, we've been going 22 minutes on this presentation, so I'm going to break it, even though there's not that much more to do. So I'll break it, be back with the next one later on.